We now turn our attention to galaxies. First, we'll talk about morphology and classification. You can think of galaxies as the basic constituents of the universe, obviously distinct units when you look at the sky. And the reason for that is that they're overdense by a factor of 1,000 relative to the extrapolation of their large-scale structure. And as we covered earlier, this is due to the additional collapse due to the cooling of baryons. One thing about galaxies is that they have a remarkably wide range of properties, and yet there are some regularities among them. Both the wide range and the regularities are indicative of different processes of galaxy formation and galaxy evolution. In some sense, they represent the fossil evidence of galaxy formation. To the first order, these differences in formative processes lead to the observable differences in galaxy morphology today. And in addition to measuring cosmological parameters, understanding of galaxy formation, structure formation in general, is one of the key goals of modern cosmology. A couple basic facts are that there are about 100 billion galaxies within the observable universe now, and their masses range from hundreds of million to maybe trillion solar masses, containing up to a couple 100 billion stars. The first thing that any empirical science would do is to catalog what's out there. And the catalogs of galaxies have been a basic data for astronomy for a long time. The very first one was due to Charles Messier in the 18th century. Messier cataloged a little over 100 objects. We still call them Messier in their number, or M in the number, and about half of them are galaxies. The rest of them are different kinds of nebulae or star clusters. Following him, Herschel family has produced more extensive catalogs, and an astronomer by the name of Dreyer has then recompiled those and published as the New General Catalog of Nebulae. Remember, people didn't know that galaxies were galaxies back then. And the acronym for this, NGC, is now commonly seen. You see a lot of objects. They're not just galaxies, but star clusters, gaseous nebulae, and so on. This was supplemented by a so-called index catalog that extended things further to the southern hemisphere, and sometimes you see that designation, IC, and the number. In the 20th century, people started compiling more systematic collections of data on galaxies. Shapley and Ames were among the first. Taman and Sandage followed. With the advent of first systematic sky surveys, originally the photographic ones from Palomar Observatory, it became possible to do this in a systematic fashion and go much fainter. And the most notable of those is the Uppsala General Catalog, which has designation UGC, and that cataloged all galaxies on the northern sky down to the apparent angular diameter of about 1 arcminute. Notice, this was the angular diameter selection and not magnitude selection, which is more common. UGC was extended to the southern sky using a southern sky photographic survey to ESO Uppsala catalog. In parallel, Vorontsov-Vyaminov in the Soviet Union produced what he called Morphological Catalog of Galaxies. Zwicky also had a catalog of galaxies as well as clusters. Girard de Vaucouleurs and his collaborators compiled not simple catalogs that would list positions, magnitudes, maybe diameters, but everything that was known about bright galaxies at the time. And those were called reference catalogs, ending up with the third one of those. And those are sort of the last pre-modern compilations of Galaxian data. Nowadays, it's all done in fully automated, objective fashion from digital sky surveys, and modern catalogs of galaxies contains tens to hundreds of millions of objects. So after you catalog what's out there, the next step is the superficial morphology. This was sort of like biology was in the Linnean days. You do not yet understanding of what's going on, but you see that there are differences. And indeed, Edwin Hubble was the first one to address this in a somewhat quantitative fashion, and a lot of his early work is still relevant today. He proposed what's still used as Hubble classification or Hubble types in a popular book, The Realm of Nebulae. And that led to famous tuning fork diagram, which I'll show you in a moment. Hubble's classification was subsequently refined or extended by the Couler, Vandenberg, and others, but the basic things haven't really changed. These days, we actually classify galaxies in a more quantitative fashion using correlations and distributions of their physical properties rather than superficial appearance on pictures. Although it turns out that that superficial appearance on pictures or morphology does correlate with a number of real physical or astrophysical properties of galaxies. And we'll talk about that in more detail. Another thing you noticed about galaxies is that they all seem to have a limited subset of subsystems, building blocks. And for example, bulges, which also look like elliptical galaxies, and disks with spiral arms. It turns out that these subsystems in galaxies correspond to differences in stellar content, in internal kinematics, age, star formation history, and so on. And so maybe that would be a better way of classifying galaxies. So here is Hubble's famous tuning fork diagram. Hubble noted that there is one obvious variable, which is the relative prominence of the bulge component, the central reddish component, and the disk with spiral arms, which tend to be fairly blue. So he sorted galaxies from redder, the smoothest, to the bluer, which are also having more prominent disks and more prominent spiral arms. He split the spiral galaxies into two, those that showed also a bar-like structure in the middle from which spiral arms originated, and those that didn't. This turns out to be somewhat superficial, but it does have some physical meaning. So Hubble thought that this was an evolutionary sequence that goes from left to right, from elliptical galaxies into spirals, and now we think that's exactly the opposite of what really happens, but Hubble simply had no other way of telling. And so because of that, the elliptical galaxies, which are actually older, are called early types, according to Hubble. And spiral galaxies, which on average are younger, are called late types. It's a little confusing, but that's just the way the usage is. Within the elliptical family, not knowing anything else about them, Hubble simply classified them by the apparent ellipticity in the sky. It turns out that that actually doesn't correlate with anything whatsoever in terms of physical properties of ellipticals, but that's what he had. He classified spirals by the relative prominence of spiral arms, SAs being the least prominent, SC being the most prominent spiral arms. That also correlates with the relative importance of bulge versus disk. And then there are galaxies that simply look like scrambled eggs, and he couldn't classify them. He just called them irregular. Turns out that's also a very heterogeneous group of things, some of which are mergers of large galaxies, some of which are genuine dwarf galaxies with spotty star formation, but that wasn't known at the time. So elliptical galaxies account for maybe up to 20% of all galaxies these days, and most of them are found in clusters or maybe dense groups, a relatively modest number in general field. Hubble classified them according to the apparent ellipticity projected on sky, having no other physical properties to use. And subsequently, there were subcategories of ellipticals based on their luminosity. This time, giant ellipticals, central dominant galaxies in clusters, dwarf ellipticals, and so-called dwarf spheroidals, which actually are a completely different family of galaxies, but more about that later. One of the Hubble criteria for calling something an elliptical galaxy is that they have the smooth appearance, meaning no spiral arms, they have no dust lanes obscuring them, they have no star formation. Turns out, actually, elliptical galaxies have all of that. They have a lot of gas, except that gas tends to be X-ray gas. They sometimes have dust lanes from spiral galaxies they gobbled up, and sometimes they have a little bit of star formation too. So Hubble subtyped them according to the apparent ellipticity, E0s being the round ones, E7 being the most elongated he could see. Now we think that E7s actually contain disks, but without star formation. And here, a couple of examples of elliptical galaxies from our immediate extragalactic neighborhood, the Virgo cluster, M87, the central elliptical galaxy in the Virgo on the left. A lot of little dots that you see around it are not stars. They're actually globular star clusters that belong to M87. M87 has about 10,000 globular clusters around it. To put this in perspective, Milky Way has about 150. And M84 and M86, remember M is for Messier catalog, are two other big ellipticals in Virgo.